Well, good morning or good afternoon or good evening, everybody, and thank you very much for joining Taylor Hobson's Advanced Harmonic Analysis webinar. My name's Richard Smith and I'm Global Applications Manager at Taylor Hobson, and I look forward in the next 40 minutes to 50 minutes ahead to talk through with you about Advanced Harmonic Analysis. As we go through the presentation, if you'd like to ask questions, please feel free to do so. There is a button on the on your screens that you should be able to type in a question, and I'll endeavour to answer the questions as we go through or at the end. So let's make a start, and the topic is advanced harmonics. And now we're going to look just at the things that we're going to cover. So we're going to start by saying, well, what are harmonics? And then we're going to look at roundness and flatness harmonics. We'll take a look at spiral harmonics on things like ball screws and ball nuts. We'll have a look at some advanced harmonic analysis software. And then we'll have a look at an advanced harmonic standard. That's the item you can see on the left of the screen here. And then we'll have a look at the instrument requirements. So, by way of introduction, harmonics in roundness metrology. A harmonic on a circular profile can be considered as a uniform waveform, a sine wave, which is superimposed on the surface of a component. And all roundness profiles consist of a series of sine waves which, when we add them together, produce the complete profile. So let's look in a little bit more detail at that in a few minutes. But before we get there, let's just see what we use this harmonic analysis for. Harmonic analysis, we have several examples of where it's vital to the production process and to the design process, particularly of bearings. On the top right, you can see the some inner and outer races and some ball bearings. Next to it, you can see a large bearing, and beneath it here, you can see a ball screw where we're measuring the spiral harmonics. And here we can see a vacuum chuck holding a miniature bearing. And on the right, a typical instrument with active anti-vibration, a very high precision spindle, able to measure all of these parts. Let's just have a quick look at the vacuum chuck holding the ball bearing as well. So this is just a very short video clip showing a 1 millimeter ball bearing held in a vacuum chuck on the Talleyrand instrument, and we're rotating the spindle here at 6 RPM, taking in data, and when we've completed the measurement, of course, we would look at the harmonics. So we're going to consider harmonics on roundness, flatness, and spiral measurements. So what are harmonics? Well, harmonics are undulations, and they're usually produced by the manufacturing process. Any roundness profile can be broken down into its constituent parts, which consist of undulations around the profile. And you can see this example on the left, where if we counted these little undulations here, we would count 60 undulations. And we would also see a slightly lower frequency undulation here. If we count them up, there's 1, 2, 3, 4, 5, 6, 7, 8 peaks. So that's 8 UPR, 8 undulations per revolution. So these undulations are produced by the manufacturing processes and can tell us a lot about the way in which the component will function under certain conditions. And we can also control the manufacturing process with this information. So I've mentioned already the word UPR means undulations per revolution. It's the same thing as the harmonic. So when we're talking about the 60th harmonic, we would be talking about 60 undulations per revolution, or 60 UPR. And you'll see that used throughout this process, this seminar. So just starting with a single harmonic, we've got there a very pure harmonic. And it's the third harmonic, 3 UPR, and we've shown it in two different views. On the left, we can see the polar view, polar plot, and on the right, we can see the same thing as a linear view. So we've got 3 peaks, 1, 2, 3, 3 valleys, 1, 2, 3, and the same on the polar plot. But typically, a roundness profile will consist of many different harmonics of varying amplitudes, not just one like this. It's possible to get something like this, but usually a typical roundness profile is made up of many different harmonics. And so if we consider some of them, we look at the first harmonic, that is known as the eccentricity. And again, first harmonic means it's got 1 peak here and 1 valley. And we'll look at how these are generated in a minute. And the second harmonic is the ovality, and we can see two peaks, 2 valleys. The fifth harmonic, 1, 2, 3, 4, 5 peaks, 5 valleys. So all the roundness profiles consist of these pure sine waves when they of different amplitudes. When we add them all together, we get the complete profile. So harmonic analysis is doing the opposite. It's breaking down that profile into these parts, because we can see these and identify the causes of problems in our manufacturing more easily. So let's just take a few more of these. We've seen already the third harmonic just now, but let's imagine we take the second harmonic, the third harmonic, the fifth harmonic, 1, 2, 3, 4, 5 peaks, 5 valleys, and here, if we counted them, the 64th harmonic. If we took these, and all of these have different amplitudes, if we added these all up together, we would get something much more complex. And this is literally what we would get. And we can see on there the 64th harmonic, that's the higher frequency. We can see the 15 UPR, that's not quite so easy to see. And we can see a fifth UPR if we're careful, and a third harmonic, and some ovality as well, second harmonic. So as you can see, as we get more and more involved, we get more and more a realistic profile where it's more complex. Then harmonic analysis allows us to separate out these different characteristics and view them on a histogram here, which on the left-hand side shows the amplitude of each of the individual harmonics. And the harmonics are shown along the bottom here. That's why it's indicated as UPR, undulations per revolution. So, for example, that's the second harmonic. That's the third harmonic, which is 2 microns amplitude. And so we now know how significant that is. Some of them we can't see so readily in there. And similarly here, if we look at this as a real profile taken on a known part, and you can see all sorts of different things here, some higher frequencies, maybe 100 or 99 UPR around there, and also some ovality. So what harmonic analysis does is it breaks this down using Fourier transform, Fourier analysis, and it breaks it down into these pure sine waves of different amplitude. So we can see which is the most significant characteristic on the roundness profile. So sometimes you'll see harmonic analysis referred to as Fourier analysis. If you look on a drawing, sometimes it won't say harmonic analysis. Sometimes it will just say Fourier analysis. So let's have a look at roundness and flatness harmonics in some real cases. And this is just looking at a perfectly round sample, and it's perfectly centered. So there's no radial deviation here. And it's perfectly centered. The center of the part is completely coincident with the datum axis. In this case, it's the spindle, it's the rotating spindle of the measuring instrument. And here we can see a gauge which is measuring the displacement. So we're looking at the displacement in this direction. And as we rotate the part like this, we see absolutely no change, of course, in the gauge reading. So now if we offset that part by a short distance, it looks like millimeters there, but in reality this would be only microns or tens of microns on a real instrument. I've done this for illustration just to show what happens when you offset. And again, the gauge will sense any deviation as we rotate the part. So we're rotating the part now. The part center is rotating about in this case, the instrument axis. And it's producing a sine wave on the right-hand side here. And this is a measure of the deflection in the vertical direction and angle horizontally. So what does that tell us? So this tells us that the part's eccentricity, and it indicates how well we have centered the part on the instrument. It's always important to make sure that we center parts before we measure them, and this is a useful indication of that. This amplitude from the center to the peak is the eccentricity value. Now, we don't just have to be looking at the eccentricity to the instrument axis. We might want to refer it to another shaft on the assembly that we're measuring. So this is another use of this. But when we're talking about eccentricity, this is a different example here with a datum axis, and here's the profile. This is the reference circle that defines the center of the component. And you can see how that is related to the axis, the spindle axis or the part axis around which it's rotating. And as well as knowing that distance, we can also, that's the same distance there, the eccentricity, we can also tell where that profile center is relative to the datum. So in this case, it's 130 degrees from the datum. So we're measuring from here around to there. And that's what we're looking at there. And that's called eccentricity position. It's a parameter associated with the eccentricity value. Let's move on now to the second harmonic. This comes typically from a poorly leveled component where if we have something that hasn't been aligned properly, and especially important on very small parts, as the parts become smaller, it becomes more and more critical. If we're not centered, again, this is exaggerated. If we're not centered, we will produce an oval shape rather than a perfectly circular shape. So the second harmonic can tell us how well aligned our part is. But it could also be, as is the case in a piston, for example, it could be that the component itself is really oval, or it could be that the component has been machined not square, out of square. So ovality can come from two causes. One is from the measurement process being incorrectly aligned, or from the production of the part where things are machined incorrectly, or some parts are deliberately designed oval themselves, such as a piston. Third harmonic here, another example, is for workpiece holding. We've got a chuck there holding a component, and what's happening is here there is too much pressure being applied to this component, and this stress on the component causes this lower order harmonic, the third harmonic in this case, because there are three jaws to the chuck, and you can see 1, 2, 3 areas where that has caused the problem. And so we say that's the third harmonic, or a trilobed component. And again, that's come from the manufacturing process. Another cause of the third harmonic is centerless grinding, where the forces of the wheel and the thing holding the part, there are forces put onto the component which create a very characteristic shape for centerless ground parts. So this can tell us a lot about our manufacturing process. Another example here for the fourth harmonic, this time, is for a cylinder bore. On a cylinder bore, if we over tighten the bolts, then what happens is the material gets pulled outwards, and you can see that's what's happened here. Here are the 4 bolts, 1, 2, 3, 4, and in each case it's pulled the material outwards, and so we get the fourth harmonic. Looking at higher order harmonics, this is an example of machine tool chatter, and in this case it's caused the 8th and 60th harmonic. A lot of that will depend, the actual values you get will depend upon a number of things, including the actual rotational speed of the machine tool. So in this case we've got 2 characteristics which, if we counted these up, we would see 60 undulations, and again we can see the 8th harmonic all the way around here. Now, it isn't always so obvious as that, but harmonic analysis can allow us to separate those out, to see really how much of this 8th harmonic we have, how much of this 60th harmonic we have. And so here it is in this particular case. What it's saying is, here is the histogram, the harmonic histogram, showing that the 8th harmonic has a micron of amplitude. Amplitude is measured from the center to the peak. Can also be expressed as wave depth from the peak to the valley. And the 60th UPR, the 60th harmonic, is at 0.5 microns. So moving on to another example of high order harmonics. Here we have a grinding wheel rotating at 6,000 RPM and a component rotating at 100 RPM. But notice that the grinding wheel is actually eccentric to the axis. So the axis is here and the center of the grinding wheel is here, and we can see that it's eccentric. So every time this component rotates once, this will be hit, if you like, 60 times by the grinding wheel. And that is actually what's happening. The shape of the grinding wheel actually gets indented onto the component 60 times. Now, looking at this profile here, it looks as if you can't really see that indentation, that concave indentation, due to the shape of the grinding wheel. But in reality, what's happened is that because we've magnified this surface so much, but we haven't magnified the radius, it ends up looking as a sort of triangular shape. If we could make this graph much, much bigger, many thousand times bigger, we would actually see the indentation. And if we display it as a linear profile, we will actually see that and be able to measure those indentations. So that's what's been caused here is the 60th harmonic because of the eccentricity of a grinding wheel and related to the ratio of the speeds. Different measurements here. These are the flatness measurements, and we're considering here a brake disc where we have a caliper on the brake disc, and the interaction with the caliper of the brake disc is affected by the thickness of the brake disc. So what we're trying to measure here is the thickness variation. How does this thickness change as we rotate the brake disc? And so we take 2 measurements, or set of measurements here. Just 2 are shown in measurement A at the top, and underneath here, side B, we take a measurement here and we get the profiles. These are the linear profiles of the polar trace. And what we're doing here with the thickness software is looking at the difference between these. This difference is indicating how the caliper interacts with the brake disc. But rather than just looking at the profile, we can take it a step further and analyze it with harmonic analysis and see what frequencies and what problems are being caused by the thickness variation of the brake disc. So as just a quick summary here, the first harmonic can be eccentricity to the instrument axis. It helps us to set up the component, or it could be on a sample, it could be the eccentricity of one section of a shaft to another datum axis. The second harmonic is ovality, and that can be measurement setup error if something is tilted, not aligned properly, or it could be a truly oval sample, or it could be something that's been machined out of square and therefore is oval. The third to seventh harmonic, typically these are workpiece holding, and we saw an example of that with the 3-jaw chuck. The 7th to 15th harmonic is typically the instability of the machining process, and about 15th harmonic upwards, it's the reaction of materials to each other and or the machine tool chatter. So we'll move on now to have a look at spiral harmonics. And before we can measure something that's a spiral, such as a worm gear or a ball screw or a ball nut, we have to make sure that we've aligned it properly. And we've got two examples here. One has got a plain shaft area at either end, and the other hasn't got anything actually. So we need to make sure that it's aligned. Otherwise, when we trace around the spiral, we won't be keeping properly on the track. And in the right-hand side, we've actually aligned on the thread itself. On the left-hand side, we've aligned on the plane shaft. So alignment is very, very important first. And so we need to be able to measure the ball screws and ball nuts, in particular, ball screws and ball nuts, very, very precisely. And to do that, the system itself, the measuring instrument, must have a low noise capability. Otherwise, we won't be able to distinguish between the noise of the instrument and the noise of the parts themselves. One way of verifying that is to look at a Taylor Hobson harmonic standard or other harmonic standards. This particular harmonic standard, though, does allow us to measure up to very, very high UPR, and it will verify what we're seeing on spirals as well as on plane bearings when we're taking simple roundness measurements. Let's have a look at the spiral measurement. So we're measuring the thread harmonics, the measurement of the harmonics around the helical shape here, and the stylus tip there is a 5-micron conisphere diamond tip, and we're keeping on track at a certain point around this track. This is the contact point of the ball bearings that sit in here, and there's one on the upper surface as well. If we measure them separately, the lower track and the upper track, it means that we are able to better define where the errors are coming from. And so from this, we can then look at the waviness or the harmonics around the surface. And this is the typical result. This isn't the whole of the thread, but this is just one lead, one spiral, shown as a polar plot. Also shown with it is the RQ value, which relates to the noise level in certain bands of UPR and certain bands of frequencies. And also the same result shown as a linear plot. And again, now analysed as harmonics, analysed for harmonics, to reveal what characteristics we have on that ball screw. And you can see we're talking here about 300 nanometers, 0.3 microns here. So the harmonics we're seeing are very, very small. These here are the tolerance bands, and all of them seem to be appearing well within the tolerance band, very, very low values. And that's exactly what we need for a ball screw or a ball nut, where we're particularly concerned with vibration or noise. And the same data here is shown in the harmonic amplitude table. So let's have a look now at harmonic analysis software. And we have the ability to color code these and say whether we've got a pass, a warning level, or a failure, a pass, failure, or warning level situation. And we're able to also look at the harmonic rankings, the importance of those harmonics relative to their tolerances. And we're able to use a formula to define the tolerance bands, or to import a CSV, a comma-separated variable file, to define these tolerance bands. There's the harmonic ranking table. And so now let's have a look at the advanced harmonic standard. So on the right here, we can see the picture of the advanced harmonic standard. And this is a relatively new standard. There is another one now available with 100 UPR. And this is able to verify that this system you're measuring on is giving the correct results, because the harmonic values that we're looking at are quite low, particularly for the higher order harmonics. So the values we've chosen to put onto this standard are traceable. They are realistic, representative of the harmonics that you would see on a typical bearing, surface. The example shown here is the 15th harmonic, the 15th UPR, 15 undulations per revolution, 1, 2, 3, 4, 5, 15 UPR. And these are machined onto these different bands. Let's have a look at the video of this measuring it. So we've got the harmonic standard here being measured. If I stop there, we can see the different bands, the results from the different bands here, and we can check the values of the harmonics, either having a look here, in this particular case, having a look at what the results look like, but also looking in the histogram to see that the values match the certificate. One other thing when we're measuring harmonics, or indeed the harmonic standard, is to make sure that we've got the right size stylus tip. And so in the top case, obviously clearly these ball tip is not going to go down into the valley, and we're going to not get the correct data. But by choosing the right stylus tip, we can faithfully reproduce the harmonics that we're looking at. So using a smaller tip for higher harmonics is very important. So this is an example using that harmonic standard of measurements taken on a roundness measuring instrument, in this case a Talleyrand instrument, and we have here the actual values from our UCAS laboratory from the harmonic standard, and for each of these harmonics there is an associated amplitude with an uncertainty value given as well. And measuring a single plane on a, just like we've just seen in the video clip, we get these results, and these are very, very typical. We're only a few nanometers different from the measured results, and that's for single plane measurement. But also if we measure a spiral on the harmonic standard, we're also getting extremely close results to the harmonic standard. So it isn't just the numbers though that matter, and this is what really matters here. This is just one of them. I've chosen the 500th UPR here, and we've measured it in a spiral on this harmonic standard. and we're only varying by 3 nanometers from the traceable standard. But that's not just the important thing. The important thing is here that there are no other harmonics here shown. There's no sidebands, there's no energy from these harmonics displaced onto other harmonics, and that's a very good indication of the quality of the instrument that's doing the measuring. So to be able to achieve this, we need certain things, certain characteristics on the instrument that we're using. So let's have a look at the key requirements for measuring harmonics precisely. We need a low noise, stable environment. In this particular case, the instrument shown on the right has active anti-vibration, and it has a very, very stable frame, able to measure harmonics very accurately. We need a high precision spindle to rotate the sample, and a high performance gauge, able to cope with the higher harmonics. And we need to use the correct stylus and the stylus tip and the correct stylus force. And we need enough data points to be able to measure the harmonics. If we're considering higher order harmonics, for example, up to 1500 UPR, we need sufficient data points. This instrument will provide 72,000 data points, which is more than enough to be able to assess that sort of order of harmonic. And the sample data needs to be regularly spaced, so the way the data is taken in is important and analysed. And we need a traceable harmonic standard and other standards in order to validate the system. So that brings me to the end of the seminar, and I've got some questions here which I'd just like to go through. And firstly, though, to say thank you very much to everybody so far for listening. And let's have a look at the questions. So the first question is it possible to modify one order harmonic in isolation? What are some ways to modify the harmonics? I'm not quite sure I understand the question there. I think modify one order in isolation. Yes, the harmonics are showing what the product produced are by altering the manufacturing process. We're able to monitor the harmonics and reduce them. So, for example, if we've got a problem of vibration or machine chatter, we can adjust the production machine in order and monitor the harmonics and to bring those values down. I'm not sure I've understood that question properly, so apologies to whoever wrote that. What is the recommended system noise for harmonics measurement? Okay, it depends what level that we're looking at. If we are looking at what parts we're looking at and the tolerances involved. On the systems here, if we were looking just a minute ago at the harmonic standard, and we're talking below just a couple of nanometers of unwanted harmonics, if you like. So we are able to discriminate right down to several nanometers. And the next question here is, can we measure harmonics on an old Talyron 73 instrument? The answer is you could measure to a certain level, but it will be limited because we don't have an encoder built in that actually tracks exactly where the stylus is as it rotates. So not just that, but the older style of instruments, whether they're from Taylor Hobson or from other manufacturers, and the older methods were used by timing the measurement. And to a certain order of harmonics, yes, you can get some indication and it's totally valid. But it's just being careful with the higher order harmonics, having enough data points and knowing where those data points are. Otherwise, we will see unwanted harmonics coming up. So the answer is yes, but to a certain degree. Now with modern instrumentation, with an inbuilt encoder, we're able to measure much higher order harmonics. Okay, well, that brings me to the end of the webinar. Again, thank you very much for listening. If you'd like to write in with more questions, please do, or contact me. My name's Richard Smith, and my email address is richard.smith@amatec.com. Thank you very much, and goodbye.